Well, welcome everyone to our colloquium, and it's a huge honor for me to introduce Roger Angel. And I'm going to try very hard to embarrass him with this bio. So Roger is a Regents Professor of Astronomy and Optical Sciences here at the University of Arizona. He graduated from the University of Oxford with his bachelor's degree in '63, and then received his MS from Caltech in 1966, which is my PhD alma mater. And it must have been a heck of a master's, because in only 1 year he got his PhD back at Oxford after that. So.
No, it's just Caltech was very slow in issuing it.
I see. Okay. And then after 6 years as an associate professor in physics at Columbia, UA was really lucky to get Roger out here to Tucson on our faculty in 1973. Roger is a member of the National Academy of Sciences, a fellow of the Royal Society, a fellow of the American Academy of Arts and Sciences, a former MacArthur Fellow, and an honorary fellow of St. Peter's College at Oxford. And he's also the recipient of the Newton Lacey Pierce Prize, the Joseph Weber Award, the Joseph Fraunhofer Robert M. Burley Prize, and the especially prestigious Kavli Prize in Astrophysics. And Roger's made himself and the University of Arizona famous for his innovative concepts, technology, and manufacturing facilities to make the largest and most powerful astronomical telescope mirrors in the history of the world. And I'm especially pleased to have Roger here at the university, so this is off my script, because he's really introduced a culture of making things. So science is a contact sport, and I think Roger's been a real champion of that we don't just talk about and analyze things. If you really believe in it, you go out and make them, and that's one of the things you're going to hear about today. I'm also very happy that Roger's been an especially strong supporter of the College of Optical Sciences, and recently, as enabled by his generous donations with his wife Eleanor, OSC was very, very proud to be able to name an endowed scholarship for Roger, the Roger Angel Graduate Student Scholarship in Optical Sciences. So today, Roger's working in novel approaches to harvesting solar energy using high-performance photovoltaics in conjunction with large, mass-produced and self-supported glass mirrors. And in 2009, Roger founded the company REhnu, where he's currently CTO, and he's pursuing the commercialization of these technologies. And that's a lot of what you'll hear about today in Roger's talk entitled Focusing Optics for Solar Energy. So please give Roger a warm welcome.
Well, thank you very much. Is this thing on and working? Okay. Well, it's wonderful to hear those kind words. I hope I won't destroy your warm feelings by my performance this afternoon. But today's been kind of a day from hell because of our startup company. We had at 7:30 this morning, we had an investor meeting trying to raise money. We did raise maybe $250,000 or more. We had a board meeting which just ended a few minutes ago, and now I'm trying to remember what it was I was going to say here, but I'll try and hold it together. So it's been a great pleasure working with grad students from the college here over the years, and this is I've listed some of the current students, and I will make an appeal at the end. We are looking for new, excellent graduate students. I have to say that Brian Wheelwright just got a job he absolutely couldn't refuse at Oculus, and Blake went off to Apple. So if you work in the group, you don't have to do solar, or I wish you would, but people have gotten good jobs. Dima Rashidko is here now. Justin Hyatt's just about to join, but has already started. So this is a summary, and we'll go through this as we go along. But if you're in optics, what I'll be talking about is solar energy. It's this huge issue to get the cost down, the final bit, so it's truly competitive with fossil fuel. And it seems quite likely that optics in one form or another, and maybe big optics, may be the key to getting that final push so that no subsidy, no nothing, solar wins out. and we'll talk about that. I will talk about a couple of ways that we've worked on that have the potential to make that breakthrough. In particular, one of them that the company REhnu is really working on to commercialize. But this is by no means the full spectrum. The sun emits light, and our job is to turn it into electricity at the lowest cost. Flat panels do a pretty good job, but there are many other ways where you can actually use optics more aggressively than you do in flat panel that have the chance to bring the cost down, to make it work at night as well as at day, and so on. So I would urge any of you who are thinking what to do with your education in optics, this is a very interesting direction. So I'm going to touch on all these things which you probably read, but so I'll get started with the main slides. There is a heritage, and Tom talked a little bit, but as both in optical sciences here and in Stewart Observatory, there's a real history of not just the academic part of optics, but actually doing it down in your shop here originally, and then in the Mirror Lab. And we do right here on campus make optics of all sizes, including the biggest in the world. And for those of you who haven't seen it, this telescope in Arizona on Mount Graham is the world's biggest. And it's 2 mirrors at 8.4 meters each, the biggest mirrors that anybody makes. And the Mirror Lab supplies about half the world's mirrors for big telescopes. So it's actually a real manufacturing, big-scale effort that goes on here just 100 yards away. I want to say before I switched over to solar energy about 60 years or something like that ago, I was most interested in planets of other stars. It's one of the big things in astronomy, and we've been thinking about it for a long time. This is a picture of a planet of another star obtained with the LBT. And what the LBT does uniquely and has unique sensitivity in the near thermal infrared. So here's a spectrum obtained with the LBT. This is going from 1 to 5 microns. You can see it's nothing like a black body. It's all chopped up by the molecular content of that planet's atmosphere. And so you can, from the spectra obtained from the LBT, you can say what molecules are there and so on. It's a fascinating area, but not fascinating enough to hold me because so we can see molecules in the atmosphere of other planets. If the aliens are looking at this planet, they would, when the light finally gets to them, notice that in the last few years, carbon dioxide has enormously spiked in a way that it never has done. This is the last 500,000 years. And in black here is the carbon dioxide content of the atmosphere, going from 200 to 300 parts per million. And in red is the temperature of the planet, going from average temperature -8 to 0 degrees C. Those two are in absolute, very strong correlation between CO2 and temperature. So where we are now is that this is an old slide, but we just passed 400 parts per million. So if you look at what we've done to CO2 in the atmosphere compared to the last 500,000 years, it's something very dramatic. And if I'm not an atmosphere person. I can't tell you whether the CO2 drives the temperature or the temperature drives the CO2, but let's give it 50-50. So if it's the CO2 driving the temperature, we're toast, right? In the sense that if you then plot what the temperature increase that corresponds to that, it's enough to melt all the ice, which has happened on the Earth before. That causes a 60-meter sea level rise, all kinds of horrible consequences. So we can argue which is causing what, but there are reasons because we understand why the temperature has been going like this. It's because the orbit of the Earth causes more sunlight to go onto the Arctic, and that's what triggers these rises in temperature and CO2. And if there's one thing we know about what our recent rise of CO2 is, it's having dramatic effects on the Arctic. So there are lots of reasons to worry. And so let's take it seriously. Is there something that we can do with our knowledge of optics that could actually help? So what you want to hit is electricity generation, if you can cut down CO2 generation there. Automobiles are the next biggest source of CO2. Right now, Tesla is sort of inching up. We don't really have the batteries to make automobiles. But if you do have batteries, the automobiles are phenomenal in their performance, right? Electric cars are very good. So there's certainly going to be a huge push, and we may get batteries that would, if you could both remove fossil fuel from electricity generation and from automobiles, you'd make a huge difference to CO2. What you have to do, though, there's no government subsidy will make this happen. The only way for that transition to happen is if the cost gets low enough that people can make more money making solar electricity than they can by burning fossil fuel. And I just put a number here that gives you a reference point. If you can install a gigawatt plant for $1 billion, then you will beat fossil fuel. So the nominal number is $1 a watt for all your cost of installing a solar plant. And the cost of electricity, if you do that, is significantly less than $50 per megawatt hour. And just remember that for the next slide. So PV panels are very good at what they do. They're very mature. Their price isn't going to change very much. And in fact, they're not anymore the dominant cost of making solar electricity. So let's use everything we've learned about optics and try and think what we could do to get the last push with solar. This is from The Economist just a couple of weeks ago. It's the relative cost of solar and fossil generation of electricity from 2000 to, this is the end of 2014. And the orange band is the range of solar costs per megawatt hour. What I said was if we can get to $1 a watt, we get to $50 a megawatt hour, which puts us about here. So you're right down in fossil fuel territory. So that's the $1 a watt, and this price is the goal where solar is already, it's about 1% of global electricity generation, and it's about $100 billion a year industry. So you can see, for those of you whose object in life is to make a lot of money when you get out of school and not save the planet, then this industry could go to $1 trillion a year or several trillion a year. So you can use your optical talent if you're smart enough to get a piece of that much action. We just, in cost, we're almost there, but you notice it's kind of flattened out a bit, and what we want to do is get this, how do we get this last factor of 2 in cost? So first of all, what is the 800-pound gorilla? So silicon panels, which were really, I think people think of them as rooftop things because that's where you see them, but most of them are actually used in utility scale plants, and they're turned on a tracker that turns them from east to west during the day. These are some panels right here near Tucson. The UA does operate the Science and Technology Park. There's a solar zone, and that's probably the most, I don't know whether it's the biggest, but it's a big plant in U.S. testing of solar panels and international testing that goes on right here. So there's maybe 20 megawatts altogether of PV and other things that are being tested. So what's the limit that we've reached with regular panels? So So they are phenomenal quantum machines, I like to think of them, and they're just amazing. A solar panel sits there, light comes in, electricity goes out, you don't have to do anything, there are no moving parts, and they are tuned to the sort of absolute quantum limits of what you can get out of silicon photovoltaic generation. And we've seen in the last few years with the push from China that the production of these has reached its limit in terms of very high efficiency, very high volume. So this is most of the $100 billion solar industry is actually making these things. But what you find is that now these are not the dominant cost of utility plants. It's more all the other things, the tracking, the land, the inverters, the permits. There's a whole bunch of stuff. So one way to get in that final factor of 2, even if these went to 0, we wouldn't get it. But if we can get more efficiency, so the same unit gives twice as much electricity, then we really have a chance to make a difference. So 20% for silicon. This chart shows as a function of wavelength. The top line is the solar spectrum. And then what you actually, at the limit, at the Shockley-Queisler limit, you turn the cream part here is the electricity you can get out. So you don't get anything for wavelengths much beyond a micron. You do pretty well in conversion efficiency at a micron, but then as you go to shorter wavelengths, it doesn't matter what HNu is for the photon, you get the same amount of energy, which corresponds to if it were a 1 micron photon. So those are the limits to converting solar. You can ask a little, this is another way of showing the data. So here's the conversion efficiency as a function of wavelength. Silicon is this right-hand curve, and we can see that for photons that are right on the band gap, you get up to 50% efficiency, but then you average this over the whole spectrum, and that's what limits you. So the best panels that you can buy from SunPower are about 21% conversion efficiency. So you can also, this is not the cadmium telluride you can buy, but this is what we're hoping at a project with ASU to get higher band gap doctored cadmium telluride cells, and they will go somewhat above 50% at their peak, which is now more like 650 or 700 nanometers. But again, if you integrate that over the solar spectrum, you still only get 20% of the total solar spectrum converted. But now you can think, so there is nothing out there at the moment in PV that does better than single panel, either silicon or, well, silicon's the best. Cadmium telluride has just got to about 17%, I think. But you can see right away, now let's put our optics hat on. What can we do that would make a panel more efficient? Well, if you are able to separate out spectrally the red and the blue at this wavelength, then you can get this average out to a micron here and then a much higher average here. So if you could just do that trick and split the spectrum at the right place, you could get 32% from these two semiconductors. It's quite a trick, though, to do that, and you have to be very optically efficient if you're going to get this benefit. If you start losing, your spectrum splitting is not very efficient or whatever, then you're going to lose out and not get it. I'm actually writing now with Ray Kostock and people at ASU the proposal that does have a trick to do this. And I would love to tell you, but it's one of the horrible things about solar. For my first 35 years at the U, I never patented anything, and everything that's done at the Mirror Lab, anybody can go in and reproduce it if they want. With solar, if you want to get investors, as we were trying to get this morning at this breakfast, they need to know that you got IP, because otherwise, if it's a bright idea and anybody else can do it, then why bother to invest? So I can't tell you too much, except that it's pretty exciting, and volume phase gratings are really interesting. as a way to do this. And if somebody wants to talk to me privately or is interested in working on this problem, I find that a lot of optical sciences students sort of look at Zmax and everything you can do with Zmax and imagine that that is a really good optical education and that tool will take them forward, and probably will. But light is actually a wave as well as being a ray, and there are many things about the wave characteristic of light that won't get done by Zmax, which are really interesting, and volume phase gratings are one of them. So I urge you to broaden your scope, because you won't find the ultimate solution, perhaps, or not all of the solutions, if you don't go beyond Zmax. So in this spirit of looking at different bandgap semiconductors and splitting the light, you can actually go to the store and buy a 42% conversion efficiency PV cell. And they're made in high volume, and every spacecraft uses these things for their solar power. How do they do it? They have three materials of decreasing band gap on top of each other. It's not always germanium on the bottom. Sometimes it's another flavor of gallium arsenide. But basically, the trick here is that the blue band gap material absorbs these blue photons efficiently. And then if you're clever about what's in the gap, the light that wasn't absorbed goes on through. And if you're really clever, you can make an electrically conducting layer. And at any rate, you get the light through for another shot in the green layer and then another shot in the red layer. That's how you get 42%. So you've filtered the light by the actual semiconductors. You don't have to have gratings and prisms or whatever it is to deliver the different colors to the different band gaps. You just put them on top of each other. So that works fabulously well. You can go and buy 42% cells. The trouble is, in space, it doesn't matter what the panels cost because the launch costs dominate. So they actually cost 100 times as much as a silicon panel. So that may seem like a non-starter if you're trying to beat the price of silicon. But there's this wonderful trick that lots of people have been looking to figure out how to make it practical. These cells, if you cool them properly, they're happy to work at 1,000 times concentration. So now per watt, instead of costing 100 times silicon, they cost 10 times less. So here is the holy grail for optics in solar photovoltaic. Can you have, and you can go to the store and buy these wonderful high efficiency PV cells. Are you clever enough to focus light 1,000 times onto the cell without blowing the budget? And that's where, as someone who's done mirrors and optics and telescopes for a long time, that seemed like a really good challenge to go look at. So I'll talk a little bit about then what we've, one solution that we're looking at that the company REhnu has picked up and that we're just getting out our first products. We sort of turned what was a lab concept into something that looks commercially viable. So people who've tried this before took what I think must have been the first idea. You make a box of Fresnel lenses, and underneath each lens you put a cell. And so, for instance, if you go out on I-10 past the tech park, you'll see some big trackers. And they have enormous boxes of Fresnel lenses in them. And they're probably close to in length, the width of this room. And they needed a huge factory to make them, and you've got to cart them from the factory to. So that company went broke a year or so ago. So that looks like it's probably not the way to do this. A lot of companies trying to do these clever tricks put their pricing as to being able to beat PV panels of 5 years ago. So when the price suddenly collapsed, most of them died. And in fact, there is no viable PV alternative at the moment to regular PV panels. But let's stick with our fundamentals. This remains true no matter how many companies have gone bust, right? We can get very efficient conversion at low cost if we can do this trick. So what we've looked at is, can we use big mirrors to collect a lot of light onto something small? And can we do it without having to build factories that make massive amounts of stuff? Well, the reason to look at this hard is that up near Phoenix in Surprise, Arizona, is a factory that makes solar reflecting mirrors, 2.5 square meters each mirror, and they cost $85 per mirror. That's silvered, painted, mounting pads on the back, and delivered to you. So this is, I think I mentioned that $1 a watt is the total budget you want to use. These mirrors would add 1/10 of that, so you can get the light to make a watt for 10 cents if you use these mirrors. And that's with today's prices that you can go out and buy them. So that sounds like a heck of a good start to your optical concentrator, is to use one of these mirrors. Now, so here's, if you've driven on out to San Diego, you pass this huge amount of mirrors. There's over a square mile of these mirrors there, about 1 million of them. Here's what a little close-up. It's very simple how you use them. You, in this case, bend the glass as a cylinder. It just sits on 4 pads, and those are stuck on by the manufacturer. And you just need a fairly light framework to support these things. In this case, it's a long trough that heats a steam pipe or heats oil down at the linear focus. And there's rather a lot of meat here because you need torsional stiffness here. But the actual supporting of the mirror, mirror doesn't cost much, and the steel to support it doesn't cost too much. However, if you want to get to 1000x, and that's where we get the price down, you can't do it by starting with a linear trough, or at least you can. I've got another student, Brian Wheelwright, has looked hard at this. So we have found a way to take light from the trough and concentrate it, but it has some issues. So fundamentally, though, you have to go, if you're using that, you have to go from 50 to 1000x. The most direct way to do that is to use not a line focus, but a dish focus, a paraboloidal mirror. So one thing that we have done at the university and have patented the technology, and then the company REhnu has picked this up, is that we have figured out how to make pretty accurate, by telescope standards about 1,000 times worse than a telescope mirror, but by solar standards twice the accuracy of any other solar mirror that's made, and it's made simply by sagging the glass into a steel mold. So we've made a bunch of mirrors this way, and they're a very good starting point for collecting sunlight. So for 10 cents a watt, we can collect sunlight to a pretty good focus, and this is our party trick where if you put 1/4-inch steel at the focus, you can melt a hole in. This was with 4 of these mirrors together and took less than 10 seconds, so it's pretty spectacular with liquid steel dropping down and so on. So we can concentrate light real well. Now you better be careful before you put your PV cells at this focus, or the same thing's going to happen to them. So the trick we've had then is check. We think we've concentrated the light for not too much money. We have to adapt this process into the plant that makes one every 20 seconds. And the company just got a $1 million award to develop this technology and get rid of a lot of this thermal inertia, get adjustment into the mold. So we're on a path that will let us put dish shaping into the very fast manufacturing process. We found a company in town, Anderson Painting, that is coating our mirrors for it. The painters never do this normally. They know all about spraying paint onto things. When we showed them how you spray and mix the 2 liquids, it's quite magical. 5 seconds, it goes on like water. 5 seconds later, it's silver. So the painters just love this. And they're getting better and better at making good mirrors and painting on the back of them. So that's a Tucson activity. Now the trick, right, how do we take our nicely focused light and get it in a form, and I'll show you here, here are some of these 42% efficient cells. And our job is to get the light at 1,000 times concentration onto these cells. This little thing is rated at 200 watts, so comparable to a full-size PV panel. So you kind of know that if you do in manufacturing to these what you did to silicon, this is going to be a whole lot cheaper. So, but you have the job then. We've got to go from this to this. And here's where knowing a little bit about optics helps. So what we put at the focus instead of the steel is we put a ball. And you can't use regular glass because it would absorb too much. But if you use pure fused silica, then you can use the ball to form an image of the square mirror that's this square mirror here. And then we've got two patterns. One deals with the ball and its magic, and the second pattern deals with this thing, which is what goes ahead of the cells here. And what it does is the ball forms a square image of the mirror at this point. And then maybe I'll pass this around if you promise not to put your fingers all over it, although it is just a demonstrator. You'll see that we have, it's called origami optics. We buy very cheap silvered aluminum, fold it, and take the light in the square. And if you look on the back, you see we've reflected it into rectangular blocks, and those exactly match the rectangular shape of the cells. So I'll pass these around. The cells don't actually work, so you can don't worry too much there, although keep your fingers off if you can. So this is a pretty good trick, right? We've taken this high-intensity light, and now we've got it onto these very efficient cells. And the trick of having this lens here is that if you mispoint, and that happens because the wind blows and the tracker moves, then the nominal rays are black here, but if you mispoint and the rays come off, the ball forms the square image in the same place. It's not very sensitive to mispointing here. And so you have a tolerance to mispointing. So Blake Kugana, who has now gone to Apple, wrote a thesis about all the optics and how they work. And this is a detailed analysis of what happens when you go off axis and how this Kohler illumination keeps the flux uniformly on these cells. You probably know if you have PV panels that if a tree shades part of a panel, you lose the juice because all the cells are connected in series. That's the same for these cells. And so it's very important when you mispoint a little bit that you keep the same flux going into each cell array here. And that's what these optics do here. And it's one of the first things when I came here as an astronomer a long time ago was that there to measure the flux of a star accurately, you can't be too sensitive to mispointing, so you use exactly these optics. So something I learned in astronomy a long time ago is actually useful. So that's one thing. So we've gone through several generations of building this type of system. Initially, it's simply a research thing, but now this is the sort of latest embodiment, which is a commercial version of this. So it's the same optical scheme, but it's the pieces that you're looking at, the origami reflector, the flat cell arrays, and they go in a gadget like this, which has 4 of the 200-watt things in it. So this is what goes at the focus of the mirror. And this generates 800 watts of electricity. So again, in terms of do we have a prayer of getting below PV panels? Well, this thing, when it's made out of aluminum, as we're using, weighs about 6 pounds. The equivalent amount of panels is 150 pounds. So in the end, if you're running a factory, is it going to be cheaper to make one of these weighing 6 pounds or 3 regular PV panels full of very high purity silicon and carefully processed and all the rest of it? It has to be that if you go through the same volume and maturity of PV panels, that this is going to cost quite a bit less. I'm halfway in my head between selling to the investors and trying to give a colloquium. Right, this is hard. But so you'll have to forgive me if I move into sell mode once in a while. But one thing you could do with this is that silicon panels have a 25-year life, and then basically you scrap them, and if you want another 25 years, you need to buy the panels over. If we don't know how long these last, they work pretty well in space, so they're probably not going to go less. But let's suppose they die after 25 years, or they go below 90% or whatever your threshold is. These cells, their Shockley Queisser limit is 70%. So they actually are getting better 1% every year. So we project that the cells that we can buy by 2020 will be more like 50% conversion efficiency and going on up after that. So if after 20 years the cells have worn down a bit in here, you can expect to go to the store and buy cells that may be significantly more efficient than what you started with. So without having to rebuild your mirrors or your steel or whatever, you can then replace just the cells in the unit here for not too much money and have another 20 years or whatever. And the utility industry normally builds for 40-year lifetime, not 25 years. So this is something that's of real interest. I better not spend too long. This is a great pleasure, because when I was talking to the investors this morning, A, they don't know any optics, and B, I only had 10 minutes. So it's nice to have a bit more. So you've seen all this stuff here. So the other guys doing concentrating PV had to build their $100 million factory. We literally can pick up the phone and order these cards. There's Solar Junction in San Jose makes the cells. We have a company in Arkansas that sticks them on the cards. So REhnu doesn't do anything except place the order, and we don't have to build any facilities or anything. These cards get made. And the industry is noticing. Sharp, who used to lead in PV before China, I think the nuclear industry in Japan sort of didn't like PV that much, and then China took over. So Japan lost its lead in PV, but Sharp was the leader. They're still a leader in making concentrator cells like this. And they have quoted us, again, to make complete cards like this, where we don't have to build any factory or whatever. So that's the unit, the power converter that has the ball and the origami optics and the 4 cards inside it. We've run all our tests so far at behind Bear Down Gym in the old swimming pool. And here's the most recent test, where now we call the unit of the mirror and the converter at the focus as a mirror module. So this is 2 mirror modules under test, and you can see the sun is coming up to the focus on each power converter here. This is Blake here, Kugana, who has now left us. And we've gone through all the steps, so now this thing turns itself on in the morning, goes to the sun, takes a day, and then closes itself down at night. And we run it for hundreds of hours in that automatic mode. So we are ready pretty much now to take these modules, put them in commercial trackers, which will either have 2 like this or 8 mirrors in them. This you probably can't read, but the gold standard of performance is the IV curve. And so this is voltage now. Each cell generates 3 volts. There are 12 of them in series. So if everything's right, you get 36 volts or thereabouts, which is what we're getting here. And if your origami optics divided the light uniformly so that every cell gets the same amount of sunlight and generates the same current, then pretty much the current is independent of voltage until you finally get to the voltage limit of the cell. So seeing a curve like this that's pretty flat along the top and then drops off after you come to the voltage of the cell means that you got the light pretty uniformly divided between the cells. So this is a sort of acid test. In this case, we generated 600 watts. The flux was 750 watts per square meter. These things are normally rated for a flux of 1,000 watts per square meter. So we can figure out the efficiency here. So this is running at 31%. We've got various optical tricks, better cells to buy. So we can see this going in a few years to 40%. And then you really are doing something that goes beyond PV panels. This is some details. I'm particularly proud of this chart. This is the air temperature in blue, and you may not be able to read this, but this is 36 or 37 C at the peak. And this is the actual temperature of the cell measured from the cell electrical properties, and that's running just a bit below 60 C. So the difference between ambient air temperature and the cell temperature is 23 degrees C. So it means we've solved this problem, right? We're not cooking the cells. We're, in fact, keeping them probably cooler than a silicon panel on your rooftop. The efficiency changes during the day, and this is a color effect. So there's one thing you have to worry about when you have a triple junction cell. They're balanced. The break in wavelength between the three is designed to keep the same current in each semiconductor, because there's just one flow of current from the front to the back. So if you don't put enough blue light in the blue cell, its current is reduced. Then you reduce the output from the whole cell. And what's happening here during the day, this is from 7 in the morning to 6 at night, is that we actually lose efficiency in the middle of the day. And that's because the color balance wasn't exactly right. It prefers the redder light of the morning and the evening and works more efficiently. When we have more blue light in the middle of the day, it's being choked by the red or the infrared cell. So there's a little bit of color balance to work on there, which we know what it is. It's coming from ion absorption in the mirror, but we're fixing that. So, sorry, another sales slide here, but sort of here's the bottom line. One thing I've discovered is that most people haven't a clue what the difference between a kilowatt and a kilowatt hour is. And this includes reporters for the New York Times, you name it. So this is a very privileged group. You're probably in the 1% of the country. Here's energy, the biggest problem that we face. And most people haven't a clue what energy is. And it's not surprising, because it's a pretty sophisticated concept, right? If you don't have Newton inside you and various other things, you don't really know what energy is. You kind of know that it costs 10 cents a kilowatt hour, but relating that to other forms of energy. So this is one of the terrible issues that we have, is that even people who want to understand the science don't know enough to know, really get their heads around what energy is. And if you don't want to understand the science, then you can. Okay, so here's the really simple picture that if you take 3 regular panels and a solar hot water heater, that's the amount of electrical and thermal power that we can get out of one mirror. So it really is a step that goes, could get us this final factor of 2. So the way it works, if you join a university like I did, every thought you have belongs to the university. It doesn't matter if you thought it up at the weekend or anything. So all of this IP and patents are held by the university, but the university wants to make money, so they will give exclusive commercialization license, particularly to a company like REhnu that spent somewhat over $500,000 in patent lawyer fees to get the IP protected on what we're talking about. So we've been showing this picture, which is an artist's rendition of what units with 8 mirrors and 8 receivers will look like. And finally, we're just a few months from actually having one of these running in the desert. and I'll show you. We were just down in Hermosillo a week or so ago, where I can strongly recommend the steak, but also the guys who make steel there. So they've made the steel frame that we're going to mount our first set of 8 mirrors on. It's gorgeous. These guys are so kind down there. We went down in the fall. We showed them our design. And the University of Sonora had guided us to this company, Sogo, in Hermosillo. And we talked to them about the design, showed it to them. And they said, oh, yeah, we think we can make that. We'll make it for free because we're keen to get your business. So we didn't think about a whole lot more about it. But then on New Year's Eve, I get an email, and it's got pictures of all this steel in it. They improved the design and then built it. And we went down a couple of weeks ago. It's all finished. It's got the slewing bearing, and it works. It's a great thing. And now they quoted us a really good price. It's what they've quoted in quantity 8 of these is $2 a pound for the finished steel, which is just extraordinary. So it's good having Mexico, very friendly people. So this is probably where we'll be getting our steel. We will certainly bid it to local makers of steel, and maybe Europe will be able to compete, but $2 a pound is a heck of a price. So this is what we were showing the investors this morning. So REhnu, several years ago, rented this piece of land in the tech park, and we've been working and working to get ourselves to the point where we could put trackers on the land. That's a picture of 16 trackers. The next picture has 160 trackers, which is a megawatt. So we now may have raised this morning enough money to make at least 8 of these trackers, which is terrific because we really then transition from these ideas in the lab to actually putting stuff that's selling power to TEP, the whole deal there. So we should make that transition hopefully this year. Well, I've got a few minutes. I just want to I spent a lot of time on this because it's obviously a big part of what I'm thinking and worrying about now. But let me touch a little bit on this is by no means the only way to do this. There are things that we've thought about, we're proposing to the DOE. Honestly, the sun is light, the cells are here. Just be clever and figure out how to get the light onto the cells, and you can do something which could do good things for the planet and turn into $1 trillion business. So, and the Silicon Valley finance people, they kind of got burnt with solar a few years ago, so they're not really following this very closely. They've sort of written off solar as a way that they can make money, but the physics and the potential remains there. So this is something I've been doing with Dima Rashidko here. So we use a single 2.5 square meter piece of glass. We are now funded to shape that glass into any shape you want and to get different shapes from an adjustable mold. So we can now, when you think about what optics you might want to feed to concentrate light, it doesn't have to be a paraboloid, it can be an off-axis paraboloid, it can be some freeform thing, and we will soon have the ability to make this. So this is a way of making an off-axis paraboloid. Normally people would steer clear of them because this is a 3x3. There's 9 of these pieces of glass in it. Every piece is a different shape. So normally you would think that that was financially not a good thing to go for. But if you have a mold where you can hit the computer and it will change its shape to the next piece, then you can do this. So what can you do here? Instead of using the ball to image the primary mirror, we can use, if we go off axis, we can use a small second paraboloidal mirror. And then the ball is really trying to form its image on a sphere, and you can sort of cheat it into going into the 4 flat PV circuit cards that we use. But this inherently wants to put the light on a flat surface here. So in terms of manufacturing, if we can get now, what have we got, 25 square meters, so we've got 25 kilowatts of light. This would melt the steel in a real hurry here. But if we put this second mirror, we can form a nice flat pupil stabilized against mispointing. And we've chosen to do that at about 100x concentration. And then you can put little lenslets in front of the cells. So this is something which maybe I won't pass around, but it's a lenslet array out of glass. So instead of having the ball and the reflectors, we would have a reflector and then a flat plate of lenslets in the cells behind there. So that's another way to go that we're looking at. With Brian Wheelwright, we're looking at yet more variants of that are pretty interesting. I have to, you're stuck between, if you want to actually build something and sell it, you can't change your mind every 2 weeks. So on the one hand, I tell my students, if you haven't changed your mind in the last 2 weeks, something is wrong. But if you're doing business, you better do something and stick with it. And this is actually pretty good, right? The fundamentals of the optics are really solid. The silica is not that expensive. But here's another way that might go. And I'm trying to figure out with a company, you'd like to be able to make IP one of your products. But it's much harder it's harder for me anyway, to figure out how that whole process goes. But I think we have to, that'll be our next step with the company. Because in fact, we are selling more brains at the moment than we are solar converters. So we are patenting everything, but the issue of how you turn that into what works for a company is harder. So this just shows, this is the square image. So the 5 meter off-axis dish gets imaged down to a 1/2 meter, pretty uniform illumination. And Dima looked at what happens if you mispoint in each direction, and it holds steady enough that we can cheat the business of getting the series chain of cells working behind this. And I'll just finish up with a little bit I've done. So PV, I think the issue of the intermittency is not a killer, right? It's going to be the cheapest way to generate during the day, and the utilities are getting smart enough now that smart grids, mixing wind, solar, some storage, whatever, that's going. However, if you have a direct way of using sunlight to make electricity after dark, that would be good. So huge amounts of effort have gone in Europe and recently in the US in building plants with mirrors that focus sunlight, that heat up liquid, that you then use electromechanical generation with a turbine and a whatever. So these two projects, the Gila Bend Trough project here in Arizona and the Ivanpah Power Tower, both cost about $2 billion. They use two different ways. I think I've got some pictures there. We will use them. They were started before PV panels went down in price. The net price was about $8 a watt. So there's just no, there isn't a very good way to get from there to $1 a watt, particularly in the U.S. where there's no premium on electricity made at night. And in fact, by the time you get to midnight, you almost have to pay to get rid of your electricity because there's no demand there. So can we be smart enough with optics to figure out how to heat stuff up and not get into $2 billion projects that are very expensive? And we have a proposal sitting with the NSF, with the DOE now, to do something like this, and I'll just finish up showing that. So the Gila Bend plant uses these mirrors, gets maybe 16% efficiency. We're going to use the same mirror, same type, and hope to get to 40%, so that's going to be much better than this. That being said, this is the most advanced thermal plant in the world, I think. It generates 200 megawatts. It does it for 6 hours after sunset. So And it has the factory, I think I said, right, is in Phoenix that makes all these mirrors. So it's brought us on a little bit. This is in Australia, so you can think about a dish, which is will put an awful lot of power to focus. But these things are pretty clumsy. It's a lot of big thing to move around. And if you want a receiver here in liquid, you've got to take your liquid all the way to the focus and then bring it off again. And it's all moving. So, in fact, big dishes haven't gone anywhere. Heliostat fields. This is the Ivanpah plant. So the virtue of it is that it puts a square mile of light onto a tower. You can see that if you were designing optics, the first thing for efficient optics would probably not be a field of mirrors every which way. And in fact, it's not very efficient. And when the sun is not, it goes all around the sky, and these things are directing the light to the tower. But the net sort of light into thermal conversion here is maybe 60%. It's not an ideal optics. And those of you who read know that there's a very big region of very high intensity which attract insects, which attract birds. So there's been a lot of play on killing birds with the thing, which is a pity. I mean, if you take any of what I said originally seriously, we could kill half the species of all creatures on the planet, which has happened in various events in the past. So to worry about a few birds getting fried is really nonsense. However, you have to get past these stages. So this is the one, just to finish, that I've been looking at with Brian Wheelwright. It's a completely new geometry for focusing a sort of intermediate amount of light to a focus. So we've got 1,500 square meters in the form of 500 panels. It's the same 2.5 square meter size that we've looked at all along. The reason we use that size is that float glass everywhere in the world is standardized to 3.3 meters wide. So you can either make a mirror 3.3 meters wide, which is too floppy and horrible, we tried it, or you can halve that and get 1.65 meter squares, and that's what everybody in the world has settled on, including us. So these are half float glass width panels. And now the motion to bring the light to a fixed focus is that we have the panels going around on a track here, and then the panels all come up and they're fixed at 45 degrees, and they go around the tower as a fixed unit. And then we have, though, a tilting mechanism on each panel that allows it to bring the light to the focus. And Brian Wheelwright has done a lot of, so this is where you do use Zmax, and if you're clever enough, you can have 550 different mirrors all tilting differently. So it pushes it a bit, but Brian has done this. You can look at how much light you can get into what size aperture at the focus, and we're able to get, even if we take an aperture that's big enough to take all the, or 98% of the light, we still have a very high average concentration, which means we can get a lot of light in a small hole, turn it into heat, and then the small hole prevents the heat getting out. So we have very efficient conversion efficiency from light to heat. We have very efficient cosine factor, so almost every square meter of glass produces a square meter of sunlight at the focus. So this is more like 90% light to heat conversion efficiency compared to 60% for the power tower. Also, it's small enough that you don't have to spend $2 billion to make one, and then by the time you built it, find you're not competitive anymore. We could build one of these pretty quickly. And there's a wonderful trick. There's a new student who's just starting here in the fall, Justin Hyatt, who's presently working with M3, the big engineering company. And he came up with this idea. So this is the configuration and operation. You don't want to put a whole lot of steel in here, otherwise you're not going to get to $1 a watt. So what do? You have, when to operate, you lift these things up with cables and lock them together. But if there's a high wind forecast, you release the cables and set them down on the ground. So this is a way of building a collector, can be lightly built, Nobody ever has to climb on it, so it doesn't have to be rated for people who are liable to fall to their death, right? This is 120 feet from here to here, so it's a long way to fall off this. So this is a very interesting thing. We'll see in a few months whether the DOE thinks it's interesting or not. And I believe that, if I get this right, well, how do I make this? Oh, here it is. Yeah, we are. So this is pushing Zmax to the limit. If you watch the mirrors, every one of the 500 is turning, so that this is just looking at elevation. We've rotated in azimuth to get the sun right, but every one of those mirrors is turning to, here's a detailed view, and you see the mirrors turning there. So that'll be in the class test for Zmax, right, to see if you can figure out how to do that. So let me just finish up, and I've said all this before. So it's a very important thing to do. It's doing well and doing good on potentially the most enormous scale. There's still other ideas that I can't touch on, how to use the mirrors that you can buy with a line focus at $85 each. Can we get those to 1000x? We've looked at a technique for there. There are some very interesting things to do with tandem PV that we're looking at now. So there is a potential, if you know optics, you know what problem you're trying to solve, there are many ways to go. So I've had enormous good research with students here from optical sciences. We're actually looking for new students for the fall, and I'm getting old, right? I want a deputy principal investigator, so any deputy principal investigators here, come and see me as well, and maybe we'll make all this happen. Thank you.